And Ajit, if I can just get a few words to test our audio here.
Sure, so welcome everybody, good evening, and nice to be here on this sunny day. That good enough? Yeah, that's good.
Perfect. I think we're all set.
We're all set, okay? Let's start now?
By all means.
Yes, good. Thank you very much. Good evening, everybody. Great to be here. And thank you, Brittany and the team for inviting me here. And also, welcome to my son Aditya. So, two of us, we basically came over from the UK. And we are here for a week. And it's nice to be here. So, who am I? I will just briefly kind of explain a bit of the roadmap today. I'm going to split it into these sections. And we'll have interactivity at the end of each section so that you don't have to wait right at the end. This is a very complex subject. Artificial intelligence in about 45 minutes is not really possible. But however, I think you will gain from this. It depends on whatever level you are at. And I will try to sort of ingest it so that everybody gets something out of this. I will share the slides with Pinkley and we're happy to share them with you. And I believe this is recorded, so I believe you can also see. So a little bit about me. I am based at Oxford in the UK. I teach AI at Oxford. It sounds very formidable, but I think that it's one of those things where you sort of end up doing. You know, that's not what your career aspirations are doing. But I think it's a great role. I love it. And also it's a very complex role, meaning that when we talk about artificial intelligence, we really push the boundaries of what we do. And you can see that in some of the work coming out of Oxford, whether it is sort of vaccines and things like this. So it's historically a university very strongly oriented on research, and that goes on to that. Within Oxford, I'm attached to the robotics department. Also specifically, my fellowship is with the engineering sciences department, which means that I take AI and apply it to very complex problems. Among others include AI with space, AI with quantum, and also AI with agriculture, which was pre-Ukraine, and now of course it suddenly has become on the top of everybody's agenda for geopolitical reasons. But we like to sort of take AI out of the algorithms, out of the maths, and apply it to real problems, and this is how I started interacting with Pinky to talk about how sort of a group of creative writers would interact with AI as a peer and would then therefore create something which is interesting. And to my mind, that's how a lot of the world is going to go. A lot of the world, especially you guys are quite young, and what you will see is you will end up not competing with AI, but rather collaborating with AI. And that's how I saw what was the class was here, and we kind of extended the partnership, and this is where we are. In terms of sort of my background, feel free to connect to me on LinkedIn. It's quite easy to find me because my name is rather unusual. And also, I have also a very strong industry focus. So I'm the chief AI officer for a German company. I also have my own research company. We work with some of the largest companies in the world. We solve very hard problems, mostly due to relating to my work at Oxford. And of course, I'm also involved, which is not here. I'm on the advisory board from the University of Johannesburg in South Africa. And I did that purposely because I wanted to democratize AI to Africa and everywhere else, generally, because I think that there is certainly a disconnect between people like us who are, I would say, among the elite of AI. And I think that needs to change. AI needs to be with everybody because it's such a game changer. Now, so I'm going to start with these basic concepts here. Yes? So, who knows this? Yes, you. This is very interesting, which I found very interesting that artists are pretty pissed off about this, that AI won something in collaboration. But what I find fascinating is Pinkley's class just does that as a matter of law. I think this is very important because I think that is exactly how the world is going to go. And perhaps the media distorts this picture. Yes, the media paints it as a dichotomy. Yes, it could be A versus B, or AI is going to take jobs or not, or something like this. But this is more like the future I see. Now, who can, this is a bit of a joke I posted on LinkedIn. Can anybody explain this? I'm just very curious to see. Maybe you could.
Yeah, well, so you've got the three-stage
So that's a very geeky Oxford joke, but that's a derivative. That's a derivative. Yes, function. That you have the first function, the beans are the function. Yes, the first derivative is your coffee sort of powder, and the second derivative is the coffee itself. Yes, so I have lots of people, even 47 people who liked it within my network on LinkedIn within a very short time. What that tells you is that we are geeks. We like maths, we like algorithms, but that's not the way it should be. Yes, I mean that's not always the way it should be, and that's the critical point. So this talk isn't going to be about this. Yes, but that is my life. That is how we create AI. But I wanted to make it more accessible in terms of how it goes. And this is mostly what I teach at Oxford. It's a full stack AI course. It's a very complex course. We work with just about everybody from Microsoft, Google, Intel, Amazon, Verizon, just about all the major companies we work with. A full stack AI, trying to understand how AI fits in and things like this. And I'm the course director of this course, been running very successfully for a while. I'm also involved in some very interesting courses, one of which is how we collaborate in thinking, and this is looking at the metaverse. Now, I'm not an expert in the metaverse. However, I have a very good understanding of how AI is used to create worlds, digital worlds. Because for us, it's a generative thing, and that's what I'm going to talk to you a little bit about. And that's how we see the world. We see AI as a sort of a catalyst to a whole bunch of stuff. And it doesn't matter if it's quantum or space or metaverse or digital twins or something like that, or even agriculture. So we see a process, we see data, we see an algorithm which optimizes the data. Yes, and that's how we see the world. And this is a reinforcing cycle. Yes, so you do this once, you do this again, and every time you improve the process. And this is basically what AI is. I mean, if you want to know the best example of that, think of Google. Yes, so if you think about Google, the Google PageRank algorithm, which is in the open source, yes, which is Larry Page's Stanford PhD, yeah, and what that essentially says is like paper publishing, yes. So I link to you, you link to me, and therefore the more people link inbound to me, the more valuable I am. And the data is owned by the individuals, but Google owns the metadata, correct? So there is an algorithm which owns the total understanding of all these links together, and there's the value there. The reason why that's valuable is because x plus 1 is better than x plus 2 is better than x plus 1, and therefore it basically every time somebody uses it, it gets better. And that's how if I work with companies, that's what I want to design, because that is what I think of AI as a competitive advantage, because that's the main difference between actually hand coding something and learning from data. And that's the sort of industry hat I put in. So the companies that work with, they typically are looking for basically world domination. Yes, it would be nice to say that when talking to their VCs, they're talking about world domination. Yes, and that's what we want to do. So this is the other side of it. Yes, I mean this is a very pragmatic view of perspective there. So this is how most of the world sees AI, sort of the 1930s job, and this is going to be true. I would not say directly of unemployment, but underemployment, yes. Certainly changing of the balance of employment for sure, I think. So it might not come down to this, but it is important to recognize this problem. This is the other one as well. So of course there is Arnold Schwarzenegger view of the world where I think everything is going to take over. This is also partly true. I mean, if you say that it put in very clearly said, whoever owns AI is going to effectively dominate the world. And if you see that in the sort of robotic, you see the Boston Dynamics, who knows the Boston Dynamics dog? Yeah, exactly. If you see these humanoid-like dogs and creatures which are getting better, so at some point they will become soldiers. And that's the thing. Yes, so that's what we're talking about here. Now, and also a little bit of hype behind it. I love this particular quote from a venture capitalist. When you're fundraising with AI, when you're hiring with machine learning, when you're implementing it in regression, you're debugging with printf. So what that means is that it depends on your audience. You always try to hype it up quite a bit. Yes? And that's very important that there's a bit of a hype behind that. Then there is a connection to statistics and how people view the world and how they change what they view and so on and so forth. So all of this is, but for me, this is an important aspect. So this is a Japanese samurai warrior called Miyamoto Musashi. My point about this is that he's a poet and also a warrior. Interesting combination in this audience, yes? So I think that what I wanted to say there is that there is a nice side to AI and there is a side to AI which is involved in not say killing, but the aggression side of it. I think it's very important to recognize that it is a multidimensional beast. And that's what I said to you, that when you talk to a company or a venture capitalist, they look upon AI in this dominating way. That's the point with that. Now I wanted to sort of start with some definitions here. So I wanted to say these definitions because people tend to misuse these terms. And I'm going to sort of explain what these terms are in detail. It depends on where you are at. You may or may not get all of these things, but you will get some of it for sure. So if you look at this video again, you will possibly get quite a bit of it. The first one is machine learning, which means explicitly training an algorithm, explicitly learning from data. Correct? So the whole point of artificial intelligence as it stands today is learning from data, and that's what machine learning is. Deep learning is something called automatic feature detection or representation learning. This definition I will explain to you further. Yes? And artificial intelligence is machines that can think and reason in theory, primarily based currently on deep learning algorithms. Yes, so these are the key definitions I wanted to start off with. And when I say AI, I mean based on deep learning, and I explain what deep learning is, and so on. Machine learning is based on traditional data. Yes. Now, what is the difference between traditional programming and machine learning? And this is an important thing. And the first thing, and the most important difference, is that in traditional programming, you are specifying the rules and you expect the outcomes, correct? So if you are coding anything using any language, you sort of you have your if statement, then statement, your for loops, and so forth. So this is where you explicitly define the logic, and of which, after definition of that logic, you get an outcome. Yes, whatever the program is supposed to do. But in machine learning, you do the opposite. Your goal is that you give lots of examples of something so that the rules are learned from the data. Yes? And therefore the outcome of a machine learning algorithm, the bottom one, is the rules. Yes, so this is what I'm trying to say to you. And this is what we will expand on, the meaning of this a little bit more. But it's important to understand that these are different things. Yes? So although, of course, to write a machine learning program, you need traditional programming. Yes, you need Python, you need some other language. But your objective in the end of the program is to infer rules from data. So far, so good. Yes? Then we're going to talk about what sort of problems to be used with machine learning or deep learning. There are certain very characteristic problems which you use, because the first thing you must realize is that this is a heavy heavy weapon or a heavy hammer or something like this. Yes, you would, if you got away with not using it, you wouldn't use it. So traditionally AI or machine learning or deep learning tends to be for certain types of problems. They include the problem is very large, the problem is open-ended, if the problem changes, the problem is hard, the problem has hidden rules, and I'll explain to you what that means. The problem has hierarchical rules, which means rules which are based on other rules which you can't infer. The problem has many variants around the core. Again, I'll explain to you what that means. The problem is generative, which is very much what you guys are doing. So you're generating something, correct? So this is the sort of classic big picture view of situations when you tend to use machine learning or deep learning. And therefore, what I'm trying to say is if you do know a rule for it, and if the rule is 100% quantifiable, you would actually explicitly code the rule. For example, temperature to Celsius conversion is a single, well-defined formula. Yes, you would not try to train a machine learning algorithm by trying to understand temperatures of Celsius and Fahrenheit and then infer that rule from the data, because you know that this is a deterministic rule, correct? So this is not a probabilistic rule. That's the key difference here as well. Deterministic things are not being touched by this. If you do find a deterministic relationship between two things, then you are explicitly able to quantify the rules into coding, and then you're happy with it. Yes, but if you are not able to find a deterministic relationship, and I'll give you examples of that as well, you will then try to infer the relationship from the data, or rather examples from the data. So far, so good. Yes. we'll take questions in a minute for that, yeah. How does it work? It works pretty straightforward. Generally, with almost all cases, you get the data, you clean the data, you explore the data, you find relationships between the data, then you model the algorithm, meaning that you build machine learning or a deep learning algorithm, and then you interpret the results. These are the basic steps, machine learning or deep learning or something like that. Of course, the devil's in the detail, which we will explain a lot more, but generally it flows that you take the data, you create a hypothesis, you clean the data, you then train a set of algorithm or algorithms, and on that you try to interpret how good that result is. Yeah. And generally it looks like this. So if you look at the classic supervised learning problem, which means that you have some data, you have some training data, you train it, you build a model, and you show it something which it has not seen before. Yes, and on that basis, it's able to classify something accurately or not, which is if it is a classification problem. Yes, which means that if you want to train it to detect spam or not, or something like that, fraud or not, you train it on lots of examples of spam data and non-spam data, and then give it something which is not seen before, and on that it interprets the result. And then you check the result, and this is how you train the machine learning algorithm. So this is generally the steps. These are the simplest ways of doing it. Where it gets a little bit more complicated is that there are a number of statistical techniques which come onto that, and they include everything from sort of Monte Carlo, Fourier transforms. Somebody mentioned Fourier transforms today in our conversation. Today I noticed that. Regression, and all these number of techniques, mathematical and statistical techniques, are part of the various algorithms which comprise machine learning and deep learning. And then there is computer science. Yes, so there is the big data aspect of it, there is the Hadoop, all the sort of MapReduce, columnar databases, the cloud, and all of these things come together. So this is what makes the whole AI problem complicated, because it has got all these sort of things which have sort of brought onto each other to create an ecosystem which is quite complex. And then there are data formats, so there is image, video, text, audio, so on and so forth, and of course, in your case, language, and language, image from language, that type of stuff. Yes, so now these modalities tend to blur. Yes, traditionally, the modalities were straightforward, so you had a time series problem, you had an image-based problem, you had a text-based problem. Now we're looking at generating images from text, from prompts, so on and so forth. And then there is the cloud, the edge. So we do a lot of work on sensor devices. We take data, we take a model, we push it onto a small sensor device, a small Internet of Things device. That's what I mean. That happens a lot with self-driving cars, for example. Self-driving cars are essentially edge devices, meaning that they're not necessarily connected. So they all run a ship, the same thing. The ship, if you run offshore, then satellite communication is your only mechanism. So historically what you do is that you build your algorithm and you push it on the ship. The ship itself is running autonomously with something. So this is how that works, yes? One final question before I take questions is that you guys are seeing, when I say you guys, it's Pinkley's group, I don't know who else is here, but I'm just addressing Pinkley's group. So you see this as a generative problem. Yes, so a generative problem is that given a data set, you are trying to generate more examples of the data set. Yes, a lot of AI is actually discriminative. Yes, so a lot of AI is actually trying to find a logical boundary between something, spam or no spam, fraud or no fraud, things like that, cat or dog or something else, something like that. Those are discriminative problems. And that's generally, I wanted to share that with you because you guys are seeing one particular aspect of AI, but the big picture of AI is different. Yeah, I can actually take questions here. Any questions on this tool? Yes.
So I have a couple of questions, but one of them kind of going back to when you were talking about employment. I'm wondering, do you anticipate sort of like a bottleneck issue like we see in some highly technical fields now where we don't have enough training or educational institutes transmitting this knowledge to a base of individuals to fill the roles of like working with AI, kind of like, I mean, the medical all that sort of stuff?
So the short answer to that is definitely yes. We already see that.
Yeah.
There is a huge demand for people with AI, and there's a huge demand for people. I was talking to this about thinking as well. I mean, a company like university like Oxford also find it hard to retain people because typically the people who recruit from Oxford tend to be Googles and the Facebooks and stuff like that. So I think that this will be a war for talent. And also there is so when people say AI, they say that they are working in AI. They're actually meaning different things, yes? So for example, if you work in a bank, yes, your entire problem may be actually a hedge fund like problem. So it's a time series problem, or it might be some kind of classification problem. But the way we look at AI is much more fundamental. So I think it's like defining new algorithms, trying to push the boundaries of stuff. So there is a range of skills within AI. That's my point. So all of them are in. Second question.
Kind of going back to the model of like one of them having outcomes and then the other one having rules.
Yeah.
So that makes me think of, in psychology, talking about neurodiverse people and the different ways that they assimilate or interact with information. And so that is something that kind of stood out to me as far as, do you feel that there is a subset of individuals who will intuitively be having collaborative relationships with AI because of the way their brain actually assimilates information?
Oh, that's a very, very detailed question. I will answer it on a couple of levels. Myself, I'm on autism spectrum, and I'm public about that. So I talked about it on LinkedIn. I mentor people that are spectrum in that. The second thing about this is that this is not a one-dimensional problem. I actually am doing some research in this area. So, for example, if you have a carer who is talking to a person on the autism spectrum, so then the person on the autism spectrum takes everything literally. This is one of the problems. So should the carer be able to deceive or be not so explicit with the truth? Or there are ways to look at that problem without. But there are also positive advantages to that. So there's a whole bunch of things around AI or PTSD. Because if you look at soldiers who are back from very traumatic experiences, they would rather speak to something which. So there is actually a whole domain called affective computing, AFFECTIVE. So the biggest company in that domain is Affectiva, which is from out of MIT, and this is funded to billions of dollars basically. And what they do is they look at AI with emotion. So I am doing a paper at the moment looking at AI for cognitive dissonance. The cognitive dissonance is not explicitly lying. Cognitive dissonance is conflicted. So there's a whole, my point is there's a whole research around that. Thank you. Yes. Sorry.
I have a question. So you brought up a case where you have machines basically learning how to walk and talk.
Yeah.
What's the projected timeline, the ultimate, like, overarching big picture per se?
Of machine being able to walk.
Yes. Is it self-autonomy or is it just to serve fixed tasks that are like more small, like?
So that's another good question. So the question is about the sort of autonomy of machines and at what point they will reach them. I think that there are many who are trying very hard for autonomous machines at the moment for various things. And if you see this thing which was from this Google engineer who talked about sentient AI, meaning AI which is conscious, and that was a hugely interesting and complex dynamic because he believed that what he called lambda was conscious and he was having a conversation with something which was real, was cognitive, yes, or cognizant, yes. So the question is that I think if you talk to certain people like Kurzweil and all those people, they believe that around 2060, yes, and they base that argument on a very specific thing, and that has to do with the ability of AI to emulate the human brain. So at the moment we are, I believe, doing the emulation of a cat's brain. Yes, so artificially, yes. And the idea is that if we extend this exponentially, we will be able to extend human level intelligence, but artificial. And that's one metric. There are a number of metrics. But what surprises me is how fast it is going. And that's one thing I'm going to cover in the last part of the talk, is to say what I look at. Because I make a presentation to my board in Oxford every 6 months, and I tell them that everything in AI has changed. And thankfully, they humor me and say, okay, what has changed? What do you think we should change? And then I tell them, so I'm going to cover 5 or 6 areas. One of them is this. Not explicitly this, but what I'm trying to say is where is it going?
Yes.
That's how fast it's going. Okay, cool. Any more questions before we? Okay, yes, sir. Yeah.
Yeah. So just one big thing that I worry about AI, because I think it is something very useful in a lot of fields. But because it's reliant on like input data from people, and people are naturally discriminatory and also like data sets are going to be from like certain sets of people. And kind of see in AI already how like it kind of ends up favoring certain traits or certain things given from the data sets. I'm just wondering how we can almost like avoid that in AI in the future to make it more.
So again, this is a very big problem and a very big question, and I think there are many smart people addressing this problem. And the good thing is there is a lot of awareness of this problem. There are 2 points to that. The first one is that it should be explainable, meaning that given a decision, you should be able to say how to do it. And the second thing is it should be transparent. The transparency is not in the code, but the transparency is in the data used to train the algorithm. Because if you actually train it with a group of people who have a certain characteristic, then of course it is going to be biased only to those people. And that's where you need a balance for that. Now, the question is, should that be regulated? And I think that I'm actually not in favor of regulation. That there is a European Union potential regulation, which is going to talk about this. But I think that in many cases, what people do not realize is that it's not intentionally malevolent in many cases. What people do is, we attribute the problem to AI, but the problem is society problem. This is the thing, yes. It's easy to blame the AI, but the data was, if you go to the bank, they have the same data, and they're actually doing the same thing. They're actually using the same data set, and this is the. Okay, thank you very much. Perfect. Okay, so I'll proceed now, and then we'll stop for a round of questions. You have a question? No? Okay, good. So, machine learning. So, what is machine learning? You already sort of alluded to this. I don't know how much you know about what depends on what you study, but basically classification is sort of separation of categories. Regression is trying to find a line or a point which fits in as many of the points. So in this case, you are trying to find something which is as close to the white circles. Yep. Attribute importance is something where you're trying to sort of understand whichever ones are most valuable. Then you do anomaly detection, which is looking at fraud detection and things like this. You find outliers from the data, and then you have cluster, which means that you try to sort of group together things which are similar, and then try to categorize within it. So these are the main broad categories of machine learning algorithms, not the machine learning, yes? And they mostly manifest themselves into straightforward data sets. So if you look at housing prices, then housing prices have certain characteristics. So for example, the number of bedrooms in the house, the proximity to schools, that type of stuff. You train the data using that, and then you try to predict the price of a house based on that, or price of or the value of salaries. That again has certain attributes, your skill level, the number of years you've got, something, and so forth. You train the algorithm using that data set and you try to predict something. So far it isn't anything magical. It looks like Excel, to be honest, and in many cases it can well be, because if your data set is not large enough, it will very well fit in within a spreadsheet, and you could very well do something which looks like that. And there's a little bit of a sort of a pipeline, the same sort of thing I explained to you before, that you take the data, you label the data, you learn the algorithm, you find and you present it new data, and those steps go on. So far so good. Yes, so this is traffic machine learning. Now we come to something more interesting, which is deep learning. And remember that I said to you that with deep learning, what you have is what I used a definition for automatic feature detection or representation learning. So the bit about, if you compare the housing prices example, in that example, you are explicitly told what the features are, typically. Yes, the typical housing prices, what influences the house price is the number of bedrooms, proximity to good schools, proximity to transportation, stuff like that. Okay? So there are these features which are influencing what the price is. And if you have enough examples of that, you can predict the price of a house which you have not seen before. So far, so good. Yeah. And there are certain things which are very unique to deep learning. And they include things such as gesture recognition, voice or biometric authentication, machine vision or computer vision, video surveillance, handwriting recognition, text generation, entity detection, detection of things within an object, natural language processing, movement prediction, creating images from text, yes, attention or sentiment tracking. The important thing about all of these and most of these is that they are not transactional data. Yes, they are typically image data or sound data or textual data, like a corpus of text. Yes, but they are not like this. They are not like this. Yes, because this actually is a much more straightforward thing to do. When you have image data or sound data or something like this, then you start to get something much more complicated. And the reason why that is important is because again we'll look at what type of problems which are possible with deep learning. Yes. Then the first category of problems is what I call modern expert knowledge. So I think people are not happy to replace a doctor, but they are happy to replace lawyers. Okay? So I say to them that you could replace a lawyer with AI, and it's actually possible to do, believe me, because the lawyer data, legal data is actually pretty much legal. Yes. So if you have a data about something and if you know whether the case was successful or not, essentially it's labeled data set, you can train something to understand that. Then you can do something called extending expert knowledge. This is drug discovery. So if you look at sort of new drugs and new medicines, they're basically permutations, combinations of protein molecules. You take a protein database and then you sort of permute it from different things, and you don't know which one of them is going to be a medicine or not. And for that, there is a bigger thing. You do clinical trials and so on and so forth. But in theory, you could have AI generate multiple combinations of protein molecules, some of which could be medicine, some of which could be not. Then you have complex planning. Now, if you look at operations research or any of those domains, AI can do that a lot better because AI can handle a very, very large number of factors and variables within that. So if you have only 10 or 15 features, the human mind can do that. If you have thousands of features, then you need something else like AI to do that. Then better communication, this includes all sorts of chatbots and things like this. New perception, meaning things like autonomous vehicles, which require a new way of learning using AI. Then there's a whole thing which comes under digital transformation, which looks at the whole enterprise and tries to change it using AI. Then there is sort of the whole cognitive or unstructured enterprise data. Then what I call a second order consequences of data, meaning if you look at insurance, insurance is a function of, for example, healthcare data. So yeah, you could have a Fitbit like thing, and then it would then be able to predict your insurance premium because healthcare data ties to your insurance data. So things like this, yes sir. Then you have problems which benefit from improved algorithms. I say this because if you look at language translation, when language translation first came around, people were not really taking it very seriously. About 5 or 10 years later, you find embassies are using language translation, yes, for one language to another, because it improved over time. So when algorithms start, they won't. So at the moment, audio is also the same thing. They have extremely good audio recognition things, but when it started, it wasn't that great. And it sort of learns over time. The final category of problem specific to deep learning or AI is super long sequence packets. So this includes things like genomics, which has basically very long sequences, which AI is able to detect, and also things like neuralites, which are very long sequences. So when neural is the long sequence, and you can probably use an example. So my point is that these are categories of problems which are unique to deep learning. Before I go into what is deep learning. Yes, so now trying to tell you that they can't be solved using traditional spreadsheet-like things. But the nature of the data here does not fit into a format which is taboo, correct? So genomic data doesn't fit that. Sort of things which I talked about here, the self-driving cars, they don't fit into that thing, but yet there is some intelligence being derived from that. Now, what is deep learning? So there's a whole bunch of things which came along to the fore, and this was one of the big examples which came along with Andrew Cole, which who now is creating a setup. But he basically detected images of cats from YouTube data by not telling the algorithm that it is a cat, meaning that algorithm was able to determine what the features are which comprise the cat, and then was able to say that this is the cat. So it wasn't, you did not tell it explicitly that this was a cat. Now, this is pretty much mainstream now, including Siri and facial recognition and so on and so forth, so all this AI stuff. But if you take a step back, so AI or deep learning is all about solving problems which are not finite domain. Yes. If you think about chess is a finite domain problem. A finite domain problem meaning that the world of chess is actually limited because it's 8 by 8 squares, every piece behaves in a predictable way. And the problem of chess was pretty much solved by computers about 25 years ago. If you look at Deep Blue versus Kasparov, Deep Blue 1, I think it's Deep Blue 1. Actually, for a computer, this is an easy problem to solve. The reason is because of the finite nature of the world. It's a commutations problem. Because the computer then can basically compute all possible permutations of the world of chess is a finite problem. Because you have only 8 by 8 squares, and therefore the possibilities are limited. And for a human they are a lot, but for a computer they're not. The problem on the right hand side is not a finite domain problem. And it's a problem that a child can solve. The problem on the right hand side is to detect that that is a dog. Yes? The reason why that is not a finite domain problem is because there are many variants around the core concept of a dog. Yes? A dog could be an Alsatian, a Doberman, a Wolfhound, a Basenji, a Dachshund. I like dogs, as you can explain. But then again, you can have dogs which are varied. They could have a collar, they could have proper ears, they could have a long tail, short tail, high fur, no fur, that kind of short, something like that. Yes. So what then happens is, one of the things I listed here right in the beginning was problems that have number 7, problems that have many variants around the core. Yes? So this is a problem which has many variants around the core because the core of the concept is a dog. But there are many variants around that. That actually is not a finite problem because it is not possible to put it in the 8 by 8 paradigm or whatever paradigm. And therefore, what you need a different type of AI to solve. Yes, and this is the crux of it. The way you do that is actually the way a child would do this. Yes, a child would think about it bottom up. So the child would look at what are the features which comprise the dog. Yes, the dog is probably friendly. It has a long tail. It has eyes. It has a nose. It has ears. It has fur, kind of stuff. So if you design AI to detect features which make up something, then you have something which automatically detects those features. Unlike the house pricing problem where those features were explicitly told you. Yes. So in this case, the algorithm is detecting what the features are, which comprise a particular entity. In this case, a dog. Yes. The way it does that is it works bottom up. Yeah. So so if you look at this as a picture on the left hand side, yes. So then you have something which is a deep neural network. Now, neural network, the idea of a neural network is basically modeled on the human brain, correct? And the way it works is that at the lowest layer, it basically detects pixels, yes. On the layer above, it detects the edges. On the layer above, every layer takes inputs from the previous one and does something more with it, adds a level of abstraction. So the layer above, or the second layer, takes the sort of edges and tries to build the contours around it. The one above then tries to have some sort of features within that eyes and head band and so on and so forth. And the last layer actually tries to classify it. So at the topmost layer, what you would have is characteristics which make up this form. And then you would say this is a person or an animal or a car. And of course, the problem here is that the first time you do it, it's gibberish, okay? Because you wouldn't notice the jump. What you then do is have an algorithm which says that this is, you tell it what the error is. You say that this is a car, a cat, a person, and then it propagates the error backwards and then continues to retrain this with lots and lots of examples, such that when it is fully trained, each layer is completely capable of identifying a specific feature. Yes, and it hierarchically builds the features bottom up. And that's what I call as representation learning or automatic feature detection. Because unlike the house rising example, nobody told the algorithm what makes up a cat. If the algorithm was trained with lots of examples of cats and non-cats, obviously, it would then be able to say, given a new picture, whether it's a cat or not. And the reason why it would be able to do that is because the layers of the deep neural network have been trained to progressively abstract features and identify something based on the features. Yes, and this is a very powerful idea because this works with anything, with sound or text, images, and so on, or video even as well. That's why it's a very extremely one of those game-changing algorithms because it is applying to so many different things, but in the simplest level, this is what it does. So it basically builds up a picture of something bottom up, and it continues to do so with lots of examples. So obviously, you need lots of examples to do. Now, the obvious thing would be that you would say that, well, but you did tell it whether it's a cat, correct? Because what you do is that, but the important thing here is that you don't tell it you tell it at a higher level of abstraction, correct? So you say that this is a cat or not, but you don't say what the cat comprises of. That is what the algorithm detects over time, yes? And this is what makes deep learning so powerful because it is able to detect hidden and hierarchical rules for something based on lots of examples of something, as long as you're able to identify it at higher. Now, this is not about cats and dogs. It works very well with tumors, for example. So this is why it's so powerful, because a tumor is nothing but an image, and it would be malignant or not, and that's what it would do. And you would do that with genomic sequences and things like that. You would all have the same thing. You would have a label of some kind, but you have these sort of comprising characterizing features which AI being from the training aspect of it. Yes? And that's why you see examples like these in deep learning things. I don't know whether you've seen them. So what it's trying to do at higher levels is trying to get things which are making more sense. So the lowest level it looks something like that, which doesn't make any sense. But when you see at the higher levels, it's sort of starting to make sense. It looks a bit humanoid, right? So this is what is happening with AI. That AI or machine learning or deep neural networks essentially are able to learn bottom up. And that's what makes it able to handle non-finite domain problems. Because that is the difference between sort of the significant difference between machine learning and deep learning. Okay. So now I'll take some more questions before I go into a little bit more of detail into this thing. How are we placed for time? You're fine, yes?
It's about 10 till 6.
Is that okay? Sure, you're fine. Okay, good. Yeah. So I can continue. Yeah, I will keep it interactive. Good. Yeah, we'll go. Okay. Any questions on this before? Yes, sir. Okay.
Yes, I come at this from a humanities and social science
Yeah.
background because I'm a professor of history
Yeah.
here at the university, and I teach with games-based learning approach. And so one of the things that I'm thinking here about is, how do we train AI to predict or to teach about values-based decision-making? Because you think about the world as it actually is out there and why humanities and social sciences and what we specialize in on that side of universities. We'd say in history, okay, X causes, these X causes then lead to this, lead to this, and lead to this. But then if this changed and that changed, maybe there might have been a different outcome. And then we then have a sort of more of a values-based debate. There's no exact right or wrong answer, but there are a range of plausible or less plausible answers, if that makes sense. And I think I'm very curious from a scientific, he invited me here today. I don't think I would have shown up, although I haven't, although oddly enough, those of you who are engineers around, most of you in the room, everybody in my family but me is really an engineering background. I'm the one that never did that. So I'm just curious how we train, if we can train, artificial intelligence to think in a non-black-white linear way, because there are problems in the world that can solve that. They can't solve that way.
Absolutely, and this is one of those big questions which I will come back to very soon with that. But the current problem with values is that values in society are time-based. Yes.
Right.
So if you look at our value and location-based, if you look at values in the Middle East, very different values here. Yes. If you look at values in the 1930s and 1850s, they are very different values today. Yeah. So the question then is, what values do we teach AI, and how would we judge which values are true or accurate? And I think this is one of those large, complex questions. And I think this is why perhaps we need people like you. Yes, I mean, I don't say that sarcastically, I say this very really.
Yeah.
Because I think that people like me tend to sort of view it in our terms. But I do appreciate the problem, and partly because I think I once sort of took it in an extreme sense to say, what would the values of AI be if it were all powerful, correct? So now we are talking about an alpha predator, which did not exist, which we as humanity have not had to face for a very long time. And then I would say, and I basically said to this person that if you look at communism and capitalism, both needed people. But if you had a very powerful AI race, it necessarily does not need people. Yes, so then your values are at the extreme end, where they question the need of humanity at all, forgetting about the relative morals of humanity. Right. So, big problem. I don't claim to have answers. I can just ask better questions as well.
It takes the whole university for that, and then some.
Yes.
Well, the question is kind of between what you were talking about and what he's talking about is just kind of where like classification and coming up with characteristics runs up against where human beings have put classifications in. Because I mean, in every field we decide this is this species, this is that species, this is this disease, that is that disease, based on what our senses are able to perceive and whatever instruments that we have. So, and then of course new problems arise. And so how do you classify it? So to think of a simple-minded example, is cryptocurrency a security? Okay, so there's all these legal rules about what securities are. Now we have cryptocurrency. There's going to be a multitude of different decision makers on any legal problem. Without AI, they would do different things and maybe eventually would have to be decided by the Supreme Court. Now AI will go in, it will have a way of classifying legal problems, and it will perhaps make recommendations. And so then there's going to be the issue of, are there good bases for these recommendations? Because I mean, there were a vast amount of data that gave up to the classifications that we had. This is a different case, and how does AI work with that type of problem?
So the question is, if obviously it has seen that. So in the end, I think that if you abstract what I've been saying generally, it is dependent on the data. Correct. So this is what I'm trying to say. And therefore, it is dependent on whatever data you provided. If it is not able to see an example of this, then it is able to. Then you have to classify it outside of that. And there is a name for this, and it is a very long form of saying that human intervention is required. It's called human in the loop. The name human in the loop basically means that human is required. human intervention is required. And this is true with lots of things which are very high risk. Okay, so one of the things about AI is that it actually works very well. We think it works very well because it is dealing with low risk problems. So for example, if you look at what advertisement am I being shown, right? So I might be shown an advertisement which is not suitable for you, not the end of the world, yes. But the more riskier you get, the more the stakes become complicated. And that's the time you start to have much more scrutiny, much more detail with it. The short answer is the higher risk I wouldn't leave it to AI. And this is what I wanted to tell you for this with this market. Cool. Thanks. Yeah. So now I'll just go into a little bit more into detail with deep learning. Some ideas I wanted to cover. Then I'll come back to the last part of it, which is basically to say what are the things which I'm looking at observe and generally overall which are the problems with that. So one of the things that AI is a probabilistic problem, and many problems are probabilistic. So for example, this thing here is basically when you look at the blue line, what it could actually be is lots of squiggles around the blue line, correct? Because what actually happens is that the stock price or whatever it is. So it's a probabilistic problem. So many problems are fundamentally probabilistic. And therefore there is an error of margin of error between them. Yes? Because what you are trying to do in this case, you're starting off you're getting this one, the one on the left, which looks very, very clean. But it was derived from things which had lots of variations around it. And then many of the problems are like that. So that's why AI or any machine learning problem is a probabilistic problem, and that is why I want to emphasize that. And let's go along with other examples as well for that. Now, if you look at what is really AI, now I said I won't talk about maths, but this is one exception to that. And this is basically that the end goal is to find a hidden function which maps two things. Yes, your x and y, your inputs and your outputs. So x is a classic in mathematics, x is the input and y is the output. You try to find a hidden function between x and y. And of course, in the case of AI, that function could be hierarchical, that function could have different rules, many things like that. In the simplest case, you would remember something like this. Yes, on the left-hand side is your equation for straight line. Many of you might remember this from your high school maths. Yes. And this is the simplest way in which you can have x and y. The equation of that is y equals to x plus b or x plus c. Again, I don't know how much of this you remember, but it's a fairly straightforward thing at school. The problem on the right-hand side is a complicated equation, a complicated representation which has no discernible equation which does that. So the potential of AI is that it's able to find the function for something which is on the right-hand side, given enough examples of it. And that could be anything. It could be a Siri, it could be X-ray detection or stuff like that. Given enough examples of something, he can basically detect complex functions. And this is the potential of AI. So if you have a little bit of a maths background, or if you understand a little bit of maths, what you understand here is the left-hand side actually is quite easy to do, because the equation of this straight line is basically a straight line equation. But on the right-hand side, there is no discernible equation function behind it, but AI can detect the function given enough examples. That's the potential of AI. Now, why bother with this is because this sort of thing is easy to do, but the more non-linear problems are very hard. So AI can detect, for example, a pattern on the right-hand side, which there is a pattern, because those sort of things which are inside the circle are classification pattern. But it isn't possible for traditional ways to detect. And this is why the more sort of sophisticated techniques of machine learning and deep learning tend to find sort of hidden patterns of that. And then again, the fundamental question is, what is learning? Right? What is learning? So I give you this example. So the whole point about learning is, if you think about a child learning to ride a bicycle, or when you first learn to drive a car, yes, you learn on a particular example. So you learn on a particular road, you drive around this car park, for example, and you learn a certain set of skills based on that. And that is the learning part. But the inference part is that you need to take those skills and apply them to any role. There's no point learning to master on that one particular role and never be able to drive on any other. Correct? So the point about whole, and this is the same aspect with AI as well, or any machine learning, is you're learning from data such that you understand the salient features of the problem from the data, such that you can infer those relationships to a problem which you have not seen before. And this is what it is, right? I mean, this is what I mean, right? You can actually understand it. It's not hard to understand if you sort of look at it with sort of traditional analogies now. And the simplest example, of course, is the linear relationship, but more complex relationships are possible there. The final thing before I finish this section is AI, or deep learning, highly parameterized model. So in the example of the straight line, there are only two parameters, M and C. I don't know how much you remember this, but M is the slope of this line, and C is the offset. In this case, C equals to 0, that's why it is passing through those axes. Yes? But those are the only two parameters we need to detect. But with deep learning, you will detect thousands and maybe even billions of parameters. Some of the stuff which we are talking about with this GPT-3 and so on has billions of parameters. And this makes AI extremely powerful, because that is actually the statistician's nightmare. Yes, the statisticians like things which are sort of discernible and explainable and so on and so forth. And now you have this billions and billions of parameters, and all you do is keep throwing compute and keep throwing data at it, and it presumably learns something. Yes, but how does it learn? Actually, is not very well fully understood. This is also a reality of it, which I will come back to that very soon. Okay. Any questions before we go to the last part? We shouldn't take us that long at all. And these are the problems that I think AI is which are very interesting set of problems. Any questions on this so far? I think we have only about 10 more minutes before we go. Yes, right.
So the goal essentially is to not just give it the linear kind of thing where you have an algorithm that just inputs information that's good, but instead take a step further where that it can make inferences on information that is seen and applied to learn skills to solve problems in various situations that it hasn't encountered before.
Right, that's right. Because the whole point is that that's why I gave you the learning to write example, right? The whole point of learning is to abstract the core knowledge behind something, so that you can apply to another problem that you have not seen. So for example, if I were to detect spam or not, right? So I get lots of fake emails, and I have learned a pattern of those fake emails. Then I go to one which I have never seen before, and hopefully I'm able to classify it as good or bad. And that's what I mean by learning something from examples, such that you learn the salience of that, but you can, so such that you can apply it to other examples you have. Yes?
You can shut this down if it's too frivolous, but so what's the difference between learning, thinking, and sentience, and what's your off-the-record, sorry about Twitch, view on the Google engineer?
Yeah, I'm just going to come to that. Literally, no, it's not from this question. It's a very important question. Yeah. So where is AI going next? Yes? Here we go. So, this is one of the examples which I think. So I was just, before I go to start, I was going to say that I had Darwin here, and I use this again to say that there are many mutations within how the AI is going. And I see this all the time. That within 2015 to now, there are 2 or 3 critical things: reinforcement learning, generative adversarial networks, and LLMs, large language models. So those 3 basically have completely changed how AI looks like, and every 2 years you find this completely crazy stuff, which asks you to go back to the drawing board, so to speak. Now, coming back to your question. Now, this is the question about sentience or things. So, the tricky bit here is that sentience is consciousness, right? And if you look at, there are some very interesting people who have talked about this, people like Roger Penrose, for example. So Roger Penrose has taken this idea of sort of understanding the sort of quantum brain type of stuff and trying to understand whether consciousness is an example of that type of interaction. You read some of that literature, but this is not something for the first time. Human beings, I think, have a desire to anthropomorphize. I'm not getting it right, anything. Yes. So to me, I think that one of the key things is that the fact that people think it is sentient is more important whether it is sentient or not. But this is actually quite important point, yes, because there are enough things people believe in which are not 100% proven without going into the sort of the ethics of it, anything from faith to religion to anything like this. Yes, none of it is absolutely quantifiably proven, but there are enough people who believe in it. And this, I think, is one of the more trickier examples, because I think we're going to see a lot more of this, because you're going to see a lot more of AI doing some amazing stuff. And people are going to believe, and there are certain cultures, for example, the Japanese culture, has a very deep affinity to things which are like that, the sort of the characters and so on and so forth. And the more cute you make them, the more appealing you make them. Again, I'm not talking about it being good or bad, I'm just pointing out a fact.
Right.
The second,
Right, and to add to that, anything that's interpretive, more interpretive based, and then all data is not equal.
yeah,
How do we train artificial intelligence to like sift through data and say, well, actually this is more valuable a piece of information than this.
so I think there you would need to pass judgment onto that. And
Right.
then that's where that's the bottom line. That's the sort of demarcation.
Right.
Should you do that or shouldn't you do that, and let it learn from how it learns? And again, there is some examples I'm going to talk about. So coming back to your question and coming back to what we have here. So there's a question which I think was more interesting, whether it is sentient or whether it is emergent. Emergence actually is a much well-defined scientific phenomenon. So if you think about emergence as an anthropology and things like that, so that phenomenon is much more understood, because there what you're saying is that local interactions produce a much more systemic result. So for example, ant colonies are able to find out the best path towards something because they are able to navigate short distances and able to communicate that information to the group, so that the group as a whole is emergent, is learning something as a whole, i.e. Where is a good place to find food, kind of stuff. Yes. So that actually is a very well studied phenomenon. There is a book called Emergence, which has been around for a while, but if you Google this, you'll see that it's a very well understood phenomenon. The question is it emergent or is it sentient? To me, that's a real question, because sentience attributes consciousness to something which is unproven, but I think the emergence may well be true. That's my answer. The second one is AI solving very large problems, such scientific problems. So the big example of that is protein folding from DeepMind. So DeepMind basically solved this problem which has been around in chemistry for a very long time, and something called AlphaFold, if you Google that. And the significance of that is that's a very big, that's like AI solving the Riemann hypothesis or something like that, one of those big unknown, eight big unknown maths problems kind of stuff. So AI being able to solve autonomously a long-term problem in a scientific domain, which in this case was protein folding, which AI was able to do, deep learning was able to do, DeepMind was able to do using that. So I think that's the second type of thing we watch out for within that. The third one is, so these are the list of problems I'm listing out as I'm looking at on my horizon, which are interesting for AI. The third one is causal machine learning. So this is a guy called Dr. Judea Pearl, who for a long time had been arguing very successfully, now people are taking it more seriously, is that machine learning actually does correlation but not causation. Yes, so it doesn't do causation. The only thing which does causation is clinical trials. Yes, or A to B testing. A to B testing is the same thing basically, that you have to say that something was caused by something. Yes, in machine learning we say that something is correlating to something. This is a very big problem at the moment, and this is something, this year in Oxford we have 2 or 3 very significant courses on this, sessions on this, because we think this is a huge thing. My own company, we do a lot of work in this space. So Judea Pearl talked about this, he's a Turing Award winner, mathematician, who talked about this in the 1980s. But only now it is being looked at more seriously in mechanisms like probabilistic graphical models and stuff like that. Again, a bit more mathematical. But the point is that it's about causation as opposed to correlation. So everything we see today is correlation, causation, and now we're kind of looking at causation. Then this one. This was the one I think you or somebody else asked this question. So the question is, can machines think and reason like humans? Currently they do not. Yes, so reasoning is a much more complex thing, yes, because it's a chain of thoughts which have to be logically connected together to infer something. Right? So when the machine learn, currently all they do is they get a set of data, they find something, they find some relationship between them. But it doesn't say that I want to go to, if I want to go to Chicago, I want to go using A to D, B to C, or I can go here or there, or I can take one route or another. To a certain extent, some of the Google Maps stuff can, but it is not able to form one inference from another. To say that if something is not working, if the train is not working, I should be able to take something else. Kind of. So now there is an interesting vision by Jan LeCun. So if you think about three sort of stalwarts of AI, people call them godfathers, but I think stalwarts is a better word. So Jan LeCun, Jeffrey Hinton, and Yoshi Bencho, three Canadians, basically. Well, they're not Canadians, all of them. Hinton is English, but they basically worked out of an institution called CIFAR, C-I-F-A-R in Canada. And they really are thinking about where AI is going and deep learning is going. And he published a very long position paper on how machines can think and reason like humans. I haven't fully read it yet, but I think it's one of those things which is people are talking about. And this, I think, was a question somebody asked here about reasoning. I think it was you. What I'm trying to say is that if you actually Google this, you will find it. And there's a link, I have the references in the back of this as well. So these are the sort of big issues. The reason why we are concerned about something like this is because the question I'm really concerned about is where is AI going? I mean, where is AI going? And then these, I think, these are the large problems of AI, and they may not be exactly solved, but we are sort of understanding something. So causal machine learning from Judea Pearl, this has been around from the 1980s, like I said. Only now are people taking it more seriously. They used to call it different things. They call it Bayesian graphs, probabilistic graphical models, and something like that. But there are significant elements of very significant use within that. Incorporating expert knowledge into AI. Why we need this is because there are problems where it is simply, because AI is essentially, machine learning is essentially a search problem. A search problem meaning that given a hypothesis space, it's able to narrow and find a particular set of hypotheses which are valid. Yes? But if you have essentially very large search domain problems, then maybe humans know something more about narrowing down that problem. And that's where you have incorporated machine learning. One of these examples is from something called Bonsai from Microsoft, which is a way in which you can effectively incorporate human expert knowledge into an algorithm. So this is what it shows you today. Quantum is interesting again. This is something we are looking at. So looking at AI and quantum. And here, quantum is at the minimum, it is a way to speed up an algorithm. And at maximum, it could be far more than that. I mean, but this is where we see it. The final one, I think the second to the final one is digital twins. A lot of my work around this space, trying to model a process hypothetically, digitally using AI. For example, if I want to model an airport, right? So I'm understanding that this is the flow of people, these are the planes coming in, that kind of stuff. And I want to say that how will this ecosystem look like 1 hour in the future, 2 hours in the future, will I see a bottleneck 3 hours in the future? So in this case, the target is not one variable, target is the whole ecosystem. Because I'm trying to model a large number of entities who are semi-autonomous and trying to predict the whole system, how it looks like. So there you do algorithms like discrete event processing, system dynamics, agent-based modeling, that type of stuff. So again, a whole different bits of AI, which we haven't talked about before. And I think this was another one somebody asked. The sort of the cognitive aspect of AI. So how much of AI is close to the brain? Yes. So if you think about the sort of the neural processing, so if you look at a deep neural network, yes. So I always tell my students, when I saw the picture of the woman with those neural networks. So no brain ever looks like that, right? No brain looks like layers of very nice neurons laid on top of each other, because that's not how. The reason why that is there is because it's computationally easy. Meaning that if you actually had a neuron connected to every other neuron, as in the real brain, it would actually never come back with a result. Computation, yes, because you have to have GPUs and things like that. So to the extent of the computation which we have to make a simplification of the structure of the neural network. Yes, but this discussion is ongoing. So how much can you sort of model the brain? How much can you try to understand that? And how much more can it? And as the computation capability grows, that's where the quantum comes in. You could potentially model more complex things. And I think the last one, no, this is it. Thank you. So we'll take some more questions.
Do you think that eventually, if we start, I mean, this can be a mundane question, but if the reproducibility crisis in scientific research, I mean, that's been a big problem in psychology and psychiatry, for example, is being able to reproduce these gold standard studies on which we make a lot of decisions.
So I think that is a problem generally, but how do you blend AI?
Well, I'm just curious if AI is able to, if like you fed AI enough data about these research studies, we were talking about like correlation versus causation, and so do you think that eventually we'll be able to solve that in the sense of not needing to have those studies?
Okay. I don't have a particular view on that. I think it's possible, but I don't know an answer to that. Yes.
I'm actually curious about like reasoning. It's very interesting how like this whole idea of like inferring information and generating information versus reasoning consciousness. And I was wondering, would there
No, reasoning is not consciousness.
no like as in like coming up with this rules.
Yeah.
Like, so my question is like, is it possible like from a humanistic perspective to allow these AIs to actually have personas? Because when you're talking about personality, in a sense, giving them, like characters in a story, right? Like, give them personality and let them run with that thread of narrative. Could that be possibly like a way to open that door for the AI to kind of like take those decisions that you were thinking about, like the maps on the Chicago idea? Could they possibly?
So I think increasingly I find AI is capable of doing many things, and some of them are unpredictable. When you would so there was a very nice article at some point where they questioned this late last year, and the question was, is scale all you need? So I was talking to Pickney about this as well. So what that means is throwing enough compute and throwing enough neural networks, will that create something which is not explicitly programmed into it? And it appears to be that is the case. And this was not coming from me, it's not an abstract discussion, it came from the guys at OpenAI, and it has been also proven by China and other countries who have large language models. What they're trying to say is that these models are able to infer information which has not been explicitly programmed into them before. So they have not been trained with the data. So what that means essentially is that some of this reasoning is happening, and we see this in GPT-3 as well. Yes, so we see that sort of little bit of an attitude or an opinion of something. Yes, and that's the challenge. So I think that there is a process of reasoning happening, and it's a much more philosophical question. I think it's almost an evolution type question. Yes, I mean if you think about evolution in general, would intelligence emerge if you had a very long time and very large amount of intelligence? Would it emerge autonomously out of something? Yes. So I think that this is an open question. I don't claim to have an answer to this, but I think that it's a good question. I think that people are leaning towards accepting it.
something that resembles what we would generally call reasoning,
Yes.
in any way.
Yes.
And so that's the difficulty, because we're actually trying to get away from reasoning in some
Yes.
way.
Yes.
And so obviously people are putting stuff in here, and it's not necessarily, quote, reasonable stuff.
Yeah.
But when you make breakthroughs in a fictional setting, frequently it's the stuff that seems least like what came before. So like when James Joyce wrote Ulysses, it just didn't seem reasonable at all. And so then how do you get there? And I don't want to ask a rhetorical question, but this is the difficulty that I've been having when I work with GPT-3. And sometimes it comes out with something really, really unexpected and charming. And I'm very prone to anthropomorphize. I don't think it's a problem. We've been doing it ever since we had cars, for sure, right? So, my van is a person, and so is my AI. But how do you get a result? How do you work with it better? Because it is difficult to work
Yeah.
with. It doesn't work with me like a person yet.
Yeah. So I think clearly there are limitations to what GPT-3 and all of these current algorithms are. So I guess my observation is, having looked at this for a fairly long time, which is at least a decade or more, which in current AI terms, it's a long time. I think I'm really surprised at the rate at which it is growing. Yes, I think that is the observation I would. And I used to start, about 4 years ago, I used to start with this class with an Arnold Schwarzenegger picture and say that this is AGI. Meaning when I meant AGI, automated general intelligence, what that means is that if you look at the Terminator 2 movie, you have this humanoid thing which sort of materializes in the human world and then goes on to autonomously live in the world and try to find the goal, which is kill the body, basically. Yes. Now, that was not possible because you didn't find AI which did multiple tasks. Yes. Now you have Gato from Google, which is a well-defined thing which does multiple things. Even GPT-3 to a certain extent does multiple things. So you have one algorithm can write code and can write scripts, correct? So in my mind, what I observed with this is not perfect. But then again, that's why I gave you the example of the language translators. Yes. So I used to know this woman was a language translator in sort of early 2000s. And she would, the first time this woman talk about it, it was like, no, this is good. My job is safe. And it's not. Nobody, well, unless you have a really, really good reason to use a language translator, you would use some form of automated translation. So that's just exactly what I would say that it's not perfect. I totally agree with you, but I think it's very interesting where it's going. Yes.
Just out of curiosity, for us who may be curious to explore AI more, where could we go for maybe additional resources or find out more information?
Sure. It depends on which perspective you want to explore it with. Knowing briefly what we met in the afternoon, I would suggest look at the more technical stuff. Yes, so if knowing what I think you do, it's relatively easy to code in Python, and many of those tools are getting easier, correct? So they are getting, especially the cloud platforms are getting easier. So if you look at the GCP, Azure, or AWS, all three are extremely good at making things very easy and integrating everything together. I would start with that. I would start because it's relatively easy to do. And the trick there, of course, is the cloud platforms obviously are a trade-off because the more you use them, the more you pay. And that's the trade-off. But from a learning perspective, you can get it because you get lots of free credits. So even if you don't need to buy something, it is not bad. You could easily get certifications at a cloud level. You could do that. If you wanted to do more detailed stuff, then you would look at something what we do, which is both very technically skill-based, but also very heavy on theory. Meaning that we talk about the maths, we talk about this sort of thing I talked about, that kind of stuff. So mostly the Oxford, what we do, MIT nano degrees, that type of stuff. MIT has something called nano degree. And people like that. That group tends to be much more, so the cloud providers or people like that tend to be much more skill-based. People like Oxford tend to be skill and theory-based. So we like theory. Yes, we like the math, we like the theory. This is how it is in that way. And I think therefore it depends on where you want to go, how you want to. But there is a ton of stuff. If you want to contact me, I'll happily share it. Yes. Something? Okay. Sorry, I thought you had a question.
I lost my thoughts, right?
No.
It's at that time of the day, I suppose.
Yeah, I know. It's a long day. But
I remember what
yeah,
it was.
no,
I remember what it was.
Yes.
I was very struck by your example of the long-standing problem in chemistry that was
Yes.
solved by machine learning. I was really struck by that because
Yes.
there are data, like really factual kind of problems that we can't solve in whatever discipline we're in. And then I was thinking about, well, this is what AI really is. If we're thinking about the next steps, the next couple layers of where AI can go, is I think we have to reconceptualize what AI is. It's not going to replace the human brain at all. It's going to be a tool to answer harder questions that we just don't have the ability to answer at this point, unless we can use this big data computational analysis.
I think that's exactly why
Yeah.
I started to talk.
So, for example, in historical studies, like it's like we're asking causation questions all the time. I don't think AI can replace that because that is a value-based way of inference. What facts are more important than the other? Things are not equal in the world. If literary studies, you're going to have a similar challenge. But what it can do is answer some of the stuff that actually stops us from asking the more profound questions. So I think this is really, really exciting. What this is really exciting.
Okay, I think this is good. Thank you very much.
Yeah.